Hello. Today I'm going to talk about two important topics. One is that we're taught in the old textbooks that electrons move in orbits around the items. Now these are actual X-ray diffraction photographies of atoms in solid state. Now ones that are in gas state might be turning, so you might see arcs, but here they are in solid state. And as you can see, the electron positions are within a range, and in fact, they're sort of little tiny arcs, okay? And here are the references for the papers. One of them is here at Rice University, which is where I'm doing the speech. All right, so now, what would make that happen? What is the subatomic behavior by dimension that gets you something that looks like this, even though the math looks like that extra 1 over r in Bohr for orbital angular momentum. So to do this, I'm going to examine each dimension independently as a more restrictive behavior within a hemispherical frame of reference. And understand that the hemispherical is 3 dimensions: the radial, the theta, which is the inclination or longitude, if you're thinking of, say, a globe. Remember, longitude goes from the equator. Inclination starts at the poles. So I use the word inclination because the first two are at the poles. That's subshell S. And so it seems much more likely that it's better described as an inclination angle. Both of those use the symbol theta. Then there's phi, which is the latitudes, which is the going around. And in that way, you can describe the position of everything on a sphere. But what's this fourth dimension? Is there a fourth dimension? No. That fourth dimension is the axis. So it's one particular radial direction that has the axis of symmetry from spinning or something like that. Okay, so when I have 4 dimensions, and those are the 4 quantum numbers, 1, 2, 3, and plus or minus 1/2, which is a hemisphere, you have a system that describes how subatomic systems operate. Okay? Now, what I'm going to do, though, is I'm going to talk about these dimensions separately. The radial dimension over here versus what happens along the latitude in these rings around the latitude. So in a subshell, we have that. Let's talk about that first. So when the rings are together, you have electrons that are spaced around latitudes in the rho phi axial plane. Now they're all attracted to this central axis, okay, by something called Bohr's cylinder surface, and a 2x for polarity, which of course is the z-axis, okay? But they're repelled from each other. So radial electrostatic is like kind repel. So these two red, but if you add up the 2 reds, that's directly outward and it's pulled directly inward. So you have a dynamic equilibrium that keeps those electrons in the shells that we see all the time. But those electrons are stuck at that distance, but they really can move a little bit. And as they move closer, obviously this one pushes them away. And if they move that way, it pushes away. So the little tiny pendulums, okay? Now these pendulums basically go around in a circle, because if I pushed all the way here, I push that one, I'd push back into itself. And that becomes a string or a ring spring. And you've heard all these things about string theory. Well, string theory is correct and incorrect. It works in just the latitude dimension. So in one of the 3 dimensions. So they overplay the hand by trying to make string theory into everything. But there's a nugget of truth in there. There are strings which are electrons based around this latitude. And of course they can wobble a little bit. The the repulsions can sort of push themselves out, rebalance, and things like that. And in that, you get something that's called the Schrodinger equation, which is position and momentum balancing out over time in these little tiny pendulums, but locked in a ring-ring set of electrons. So it's in the phi direction, and there's a general Schrodinger equation, but I'm talking about the specific ring-string solution, which then applies. You see this 2 pi, that's the multiplier to get around the circle. 2 pi r squared is the circumference of the circle. So it's as if it's a straight line. Now what happens though is funny, is those dimensions are not the actual dimensions. It has this equation that's used all the time in subatomic physics is for this distance, but the actual repulsion is there. So general relativity then takes that curvature and increases the force accordingly. And so you have to take Schrodinger equation, you have to overlay Dirac, and then you have to overlay Einstein's general relativity to get an actual calculation of how electrons behave in this axial plane. Hope that helps. Now though what happens is the radial direction. The radial direction basically is electrostatic, and by that the electron would just fall into the nucleus as their opposites attract. And as they get closer, they attract more and more and more and more. For the force or acceleration level, that's 1 over distance squared. That's what this shape of the red line here is. However, we also know that there's a separate radial force that has an extra 1 over r. Now, Bohr called that an orbit, but we know it's not an orbit. If I make that a fixed item, it is this green line. And the funny thing is that if you take the sum of those two, if you make the action 2 forces push and pull, like a standard spring, not a ring spring, that becomes something that's called Hooke's law. And you just hold a spring and it will bounce back and forth in that radial direction. But there has to be a dynamic place. Well, that's the Bohr radius. And what happens is when you sum the green and the red, it becomes the black. And at this point, there is no forces pulling it. If the distance gets too far out, it becomes physics negative. Negative, an acceleration reducing the distance back to where it was. If it gets too far, this extra 1 over far pushes it outward. So basically, this is a self-sustaining, self-settling equilibrium for electrons in shells to get what we want, okay? And then over here is what happens is the subshells, which are longitudinal rings, okay? Now, okay, if you look at that, that's very nice. It gets there, and the difference between them is 1 over r squared. So as you get further away, it's pulled, the net pulled, A over B, stronger and stronger. So an electron never actually falls into the nucleus. It hits this wall of repulsion. Matter of fact, the average location will look something like that, because you'll have some, say, pendulums that might go a long way. They have a lot of energy, lots of heat. And those that are at low temperatures, really just very tiny. So by the time you're done, you have a lot of electrons spending the majority of their time in the same place. Ah, look at that. These are actual X-ray diffractions, and they look like electrons moving a little bit, but having the majority of their time in one space. And it gets lighter and lighter, but and a very strong increase to a really bright spot. Or it's moving in that direction, but it's able to do a different sort of pendulum from a different equation in this direction. So you get something that looks a little bit like this. So in that way, I see that I have 2 equations which basically incorporate the things of subatomic physics, but in a very different way. The option of a radial regular spring and a axial ring spring creates both the behavior for this and also eventually the proof of quantum mechanics by Bose. This famous paper was written and he sent it to Einstein. Einstein translated it into German so it could get published because he thought it was so brilliant. And so when Einstein's translated your work, I think you should feel pretty good about it. Anyway, this is what happens for subatomic beta in different dimensions to explain actual physical evidence of what we have.